In 1929, Edwin Hubble made a very interesting observation about a recently discovered object in our universe: galaxies. He noticed a relationship between a galaxy's distance away from us and the amount that its light had been redshifted. Galaxies further away from us were, on average, redshifted more than galaxies closer to us, and this trend was linear. Since the redshift of a galaxy is proportional to the speed that it's travelling away from us at, this means that, on average, galaxies are travelling away from us, and their speed is proportional to their distance from us. The gradient of this graph, or constant of proportionality, is appropriately named Hubbles Constant. But what does this fact about galaxies mean? Imagine a grid with a dot in the middle of each square. This dot represents a galaxy. Now expand the grid uniformly everywhere. The dots closest to us only appear to move slightly away from us, whereas dots further away from us move much faster. Moreover, we can choose any of the dots to be our reference frame, and this will still be true. If we change our reference frame to be a different dot, we once again see that galaxies close to us move slower away from us than galaxies further away. There is no special dot. Each one can claim to be the centre, and that it's the rest of the dots that are moving around it. It's clear to see that by expanding the grid everywhere at once, it doesn't matter which dot you choose, all have this relationship that dots further away will be moving faster away. The recession of galaxies in our universe is therefore excellently explained by saying that the universe is expanding equally everywhere. But why? What is causing this? How can space expand? To understand, we must look to general relativity. General relativity treats space-time, the arena that we exist in, as geometric. Moreover, this geometry is dynamic and can change with time. The geometry is physical, and so should not depend on the arbitrary coordinates that we choose to describe it. A useful tool to measure distance in a coordinate invariant way is the metric tensor. This sounds really intimidating, but it's not, and you've actually probably used it already without realizing. Imagine the dot product between two vectors A and B. We take each component of the vector, multiply them together, and sum them. Taking the dot product of a vector with respect to itself gives its length squared, which is independent of coordinate choice. But we cannot just multiply two column vectors together. So we need something that will convert the second column vector into a row vector. This is the metric tensor. In this example, the geometry that these vectors live in is three-dimensional Euclidean space in Cartesian coordinates. The metric takes the form of the 3x3 identity matrix. However, when the geometry of the space gets more complicated, the metric tensor gets more complicated accordingly, and so therefore will lengths. In four-dimensional flat spacetime, the metric tensor takes the form of the following 4x4 matrix when we use spherical polar coordinates. The negative sign distinguishes between space and time and is completely conventional. We now ask, how can we modify this metric so that the spatial part expands with time? We simply multiply it by a number called the scale factor, A, which depends on time. As t increases, so does A, and the universe expands. It's clear from this that general relativity absolutely has a mechanism to account for the expansion of space. General relativity therefore has the capability to explain why galaxies, on average, are moving faster away from us the further away that they are from us. Okay, great, but what's actually causing this number, a of t, to increase? Einstein's field equations relate the second derivative, or the curvature, of the metric at a point in spacetime to the energy content at that same point. What we want to do is to take the metric that we've found and plug that into this equation and match it up to an energy distribution that reflects our universe. In order to do this as simply as we can, we make two assumptions about the energy distribution in our universe. Firstly, we assume that we don't occupy a special place in the universe. We actually already made this assumption when looking at the expansion of dots on a grid. This is known as isotropy. Secondly, we assume that the distribution of matter on the largest scales is roughly even everywhere, which is empirically reasonable and is known as homogeneity. With these assumptions, the solution to Einstein's field equation is known as the Friedman Equations. These tell us how the scale factor, a of t, changes with time when we have a certain matter content in the universe. These equations are really quite amazing. Let's look at them in a bit more detail. The dot refers to how the scale factor changes with time at a particular time. This is then divided by what the scale factor actually is at that time, and then this is squared. This means that if the universe is already very large, i.e. the scale factor is big, then a constant change in the scale factor will require a greater positive number on the right-hand side. On the right-hand side, we have two terms. The first term has some constants in front of it and the symbol ρ. This is the energy density, or the energy per unit volume of matter and radiation in the universe. Notice that it has a negative sign. This says explicitly that the energy of matter and light causes the universe to contract. The more matter and light there is per unit volume, the quicker it contracts. So why is the universe expanding then? The second term has a positive sign, and so this must be the term responsible for the universe's expansion. This is known as the effective cosmological constant. These two terms essentially battle each other out and ultimately determine whether the universe is expanding or contracting. As it happens, in our universe, lambda wins, and therefore our universe is expanding.